and welcome to the very first topic of this chapter. We will be learning about selection of sections. In the last chapter, we discussed how to calculate the tensile strengths of various sections. Well, in this chapter, we will discuss how to select an appropriate section from the AISC manual that can resist the factor tension load. We will start by discussing the three selection criteria, followed by slenderness ratio, and understand the selection process. So let's begin. Selection criteria. So, as a designer, you will have all the freedom to select the appropriate section for your design. But for an efficient and an economical design, the designer needs to keep these three things in mind: compactness, dimensions, and connections. Let's understand each one of them. Compactness refers to slenderness ratio of the section. We will discuss this topic momentarily. Second thing to keep in mind are the dimension restrictions of the members. For examples, where minimum clear height is required from the roof, you need to restrict the height of the section. That might affect the selection criteria of the members. Third criteria is connections. Well, some steel sections are not very convenient to bolt together with the required gusset or connection plates, while the same sections can be welded together with ease. For examples, angles, channels, wide flange sections, and American standard sections will probably be used when the connections are made with bolts, while plates, channels, and T's might be used for welded structures. Hence, the type of connection will also impact on the selection criteria. I hope it's clear. Let's discuss about slenderness ratio of a section. Slenderness ratio. According to the definition, the slenderness ratio of a member is the ratio of its unsupported length to its least radius of gyration. You might ask, why do we need to use slenderness ratio? Or where is it used in the design? Well, the value of this ratio is limited for tension and compression members, meaning there is a maximum value prescribed by the AISC that we cannot exceed. Well, for tension members, the upper limit on this ratio ensures that the section has sufficient stiffness to prevent it from lateral deflections or vibrations. You might ask, tension members have only axial tension forces. Then why consider for lateral deflections and vibrations at all? Well, during the erection of steel members that are under pure tension, there may be lateral wind or earthquake forces on the section. To account for those forces, AISC recommends us to limit the slenderness ratio. This limiting value is 300. For compression members, this ratio accounts for the steel's susceptibility to buckling. A great deal of discussion will be done in part 3 of this course. So, in short, the limiting slenderness ratio of 300 is to be kept in mind while designing a tension member. We have discussed quite a lot of theory. Now, let's see how the selection process is actually done. To make sure what we design actually performs well under the loads, we need to make sure that the strength of the section exceeds the loads applied. So, as written, the design tensile strength should at least be equal or greater than the factor tension force. We discussed this design philosophy in part 1 of the course. Well, continuing that discussion, let's derive an equation that will help us in selecting the appropriate section size. Let's look at gross section yielding. We know that the design tensile strength PR should be equal or greater than the factor tension force PU. Design tensile strength is the nominal tensile strength times the resistance factor. But from the previous videos, we learned that the nominal tensile strength is the minimum yield stress times the gross area. So if I make gross area as a subject of this equation, we get this formula. This formula means that the gross area of the section should be equal or more than the terms on the right for the design to be successful. The minimum gross area required for the section to resist the tension force is Pu over Phi times Fy. This is a very important equation. So if we are given a factored tension force Pu, we will calculate the gross area of the section required to support the force, and using the manual we can select a section that has a gross area equal to or greater than the minimum area required. I hope this is clear till now. Now we need to compute the required gross area for net section in rupture as well. We know that the design tensile strength should be equal or greater than the factored tension force. The design strength is the nominal strength times resistance factor. Note that the resistance factor to be used here is 0.75 and not 0.9. The nominal strength under rupture is the ultimate tensile stress Fu times the effective net area AE. And as discussed in the earlier videos, the effective net area is the net area times the shear lag factor. So if I put net area as subject of this equation, I get this formula. So here we got the minimum net area required to support the tension force Pu. But here I am trying to calculate the required gross area. So we need a gross area term in the equation, right? We have net area here. We know that the net area is its gross area minus the area of holes. So the gross area of the section should at least be equal or greater than the terms on the right. So the minimum gross area required for net section rupture is this formula. So till now we have calculated the two equations to compute the gross area required. The greater of the two areas will govern the design and the section is selected appropriately. But after selecting these sections, we also need to check the recommended slenderness ratio, right? As discussed before, the slenderness ratio is defined as the ratio of unsupported length to the least radius of gyration. The unsupported length is denoted by L and the radius of gyration is R. This will be more clear once we start solving some examples in the next videos. So, according to AISC, this slenderness ratio should be equal to or less than 300. So if I rewrite this equation in terms of the radius of gyration, R should at least be equal to or more than L by 300. We will use what we have learned in this lecture in the examples that will follow. See you there.